Everyone. I thank the organizers for giving me a chance to speak here. As you can see, the title is Presheaves, Enriched Presheaves and Diagrams on the Burnside 2 category. This is a joint work with Professor Rekha Santana and Priyanka Sawant. So the motivation comes from Mackie functors, which plays a central role in equivariant equivariant algebraic topology. So, go to the next slide. So, in the equivariant setup of algebraic topology, key functors play a central role. What are they? So they are ab-enriched presheaves on the Burnside category, which we are denoting by BG, and they take values in abelian category of abelian groups. Our goal is to investigate some higher versions of this Mackie functors and Burnside category. So let's first just discuss a bit about what the Burnside category is, the one categorical version of what we will do. So the objects are finite G sets, and morphisms are isomorphism classes of spans, which look like this, X, A, Y. So one can think of these as isomorphism classes given two finite G sets X and Y. A morphism between them will be denoted by a triple A, F, and G, where A will be the finite G sets in between, and F and G are the two arrows. Okay. Obviously, the identity is the isomorphism class of XXX, where the arrows are identity morphisms, and the composition is via pullback. So given a morphism between X and Y, which looks like XAY, and a morphism between Y and Z, YBZ, the composition is given by A crossover Y, B. The enrichment of the Burnside category. So via disjoint union, we can give abelian group structure to the morphism set between X and Y. So here we show the monoidal structure. So this gives a monoidal structure. So XAY disjoint union with XBY is actually given by the disjoint union between A and B. And this gives a monoidal structure to the set of spans, isomorphism classes. And we use the Grothendieck group completion to get the group structure. So we can say that the Burnside category is enriched over the category of abelian groups. This will be quite basic with regards to whatever happened today. So I thought maybe a bit of definitions would be good. So presheaves on BG are simply functors from the opposite category to BG, and diagrams on BG are functors from BG. And we can replace BG by any arbitrary category to get presheaves and diagrams on that category. So the Burnside 2 category, so it will have 0 cells, 1 cells, and 2 cells. The 0 cells are finite G sets again. We specify them by N and alpha, where N underlined is the set 0 to N. And the alpha is a map between N and N. So it gives a G action on N. I mean, N underlined, the set N. The 1 cells are the spans of G sets X, A, Y, even though the notation is same for morphisms or 1 cells. Here in Burnside category, we are taking isomorphism classes of spans, while in the 2 category, we are taking spans as it is. And the 2 cells are G maps between G sets. So compatible with the spans. So a map between A and A dashed, two G sets, will be a 2-cell if a diagram like this commutes. Okay? And the thing is, there is more to the morphism set between X and Y in this category. It is not only the spans of G sets, but some more elements to make it enriched over a particular category. So there we will whisker. There is whiskering is the word, I guess, to introduce another element which act as an identity. So since the one cells are not isomorphism classes anymore, they are just spans. Unless I introduce an identity-like element, the identity element that was there in the burnside category doesn't act as an identity element when you're trying to do disjoint union as your group structure. So we have to introduce some other element in the morphisms. Yes.
If you say two category, you mean honest to God two category, right? Like actually associativity,
Strict
actual. Okay, great.
Yes. So we introduce some identity-like element, which will be the identity for the group structure in the morphism set. So there is more to morphism set. One needs to whisker an element, identity element, to the spans to give it a structure of a permutative category. So that identity element, along with these disjoint union and pullback, that gives this morphism set a structure of strict symmetric monoidal category. As a result, we say EG is enriched over permcat, the category of small permutative categories. A thing to note that permcat itself is enriched over itself, but why I'm saying this, so when we are dealing with Mackey functors, we are looking at enriched functors from burnside category to AB, where both burnside category and the category of abelian categories are enriched over AB itself. Now we are trying to do something similar from the burnside 2 category to the permcat, and we see that both of these categories are enriched over permcat. So that's why I wrote the line that permcat is enriched over itself. So our object of interest is presheaves on EG that are permcat enriched two functors F from opposite category of EG to permcat. These can be thought of as permcat valued higher versions of Mackey functors. So we have now reached to a state where we can sort of describe what the problem is. So suppose C is the category of permcat enriched functors from OG op to permcat, and D is the category or the diagram category taking values in permcat. And the question is, can we establish some equivalence between the category and the diagram category? Yes.
Sorry, this is lagging a little behind, but if you're not taking equivalence classes of spans, how do you get strictness of the joint union on the morphisms? Like you said you had strict.
When you're composing, the composition is via pullback, and you have a choice of pullback.
Right.
So you make a choice of pullback when you're composing.
Right, but then the what is it? The symmetric monoidal category structure is on the morphisms.
Yes.
Right? And so then so you're taking a disjoint union.
Yes.
That's monoidal structure. How does
So if you're taking A and B, so suppose you have X.
Would you be able to write on the maybe under the slide, just so it's visible?
Yes, sure. Yeah. This one is fine.
Yeah, that's the.
I have X, A, Y, and I have X, B, Y, So you're putting a disjoint union structure here, and this A disjoint union B, the set itself is the same set. So in disjoint union of A and B or B and U, the set itself is the same set. So you don't have any problem while composing. Is that?
Thanks. I'll think about it. Yeah, yeah, thanks.
Okay, quickly also ask, so here when you say EG op, you mean like you
The
opt
opposite
both,
category to EG.
right? But you opt both like 1 and 2 cells, right?
Yeah. Okay. So the question is whether we can see C and D in some sort of same way. But more precisely, the question is there any equivalence of homotopy theories between presheaves and diagrams on EG? So why this problem? So we'll go back to the burnside category. So the burnside category has the problem, a property of being self-dual. So BG is isomorphic to its opposite category. As a result, Mackey functors can be both viewed as presheaves and diagrams. So they have a contravariant structure as well as a covariant structure, and these two structures are compatible with each other. So we want to just see whether this self-duality in the burnside category can be extended to the burnside 2 category. So the functor that is that realizes this self-duality is I denoted it by R, and it is identity on objects, and it takes X, A, Y to its reverse. Note that here these are isomorphism classes of spans. Now the question is, can this functor be extended to the 2 category, burnside 2 category? The answer is, no, but it fails only a little. I mean, it's not a strict 2 functor, it's a pseudo functor. So it fails to preserve composition of 1 cells. So this makes R a pseudo functor, not a strict 2 functor. So our plan is to strictify R to get a 2 functor R tilde from EG to EG up. Then we want to get a functor from C to D that is denoted by R star, and R star is given by composition. So in C, we have functors from OG op to permcat, and we compose it with R tilde to get a functor from, sorry, I said OG, EG to permcat. This is the way we want to get R star. And similarly, we can get L star also from D to C, where L is a functor from EG op to EG, but then again, it's the same functor, basically identity on objects, and then reversing. Is there any question?
Right, when you say strictify R, this doesn't involve changing the 2 categories, it's just changing the function.
Yes, it involves, but we try to get hold of it by some other makings. So if we have R star and L star, they behave like inverse equivalences. So they are relative functors with respect to some stable equivalence. I'll not go into that right now. And R star composed L star and L star composed R star are connected via zigzag relative natural transformations to the identity of the respective categories. So they form inverse equivalences of homotopy theory, but why we are talking about inverse equivalences? So a hands-on criterion, so there's a proposition by Gursky, Johnson, and Osorno that inverse equivalences of homotopy theories are equivalences of homotopy theories. Usually, if you're trying to find out equivalences of homotopy theories, you take the two categories, and then you form, you do some taking nerves and everything, you go to a bisimplicial set, bicategorical set, and then from there you have to use the model structure on bisimplicial sets to conclude about equivalences of homotopy theories. But this R star and N star, if you have equivalences of homotopy, inverse equivalences of homotopy theories, then that complicated journey becomes a little easygoing. So this result is useful because it bypasses the apparently intimidating definition of equivalence of homotopy theories. And we can just verify whether R star and L star follows easy conditions, easier relatively. Okay, so we go back to, so that was the plan. Now we'll just go back to strictification of R. So the reversal assignment, which takes x a y to y a x, fails to be a strict two functor, and it is a pseudo functor, and we attempt to replace its weak structure by strictification theorem.
Yeah, can I be confused? So it's not a two functor, is it?
It's a pseudo functor. So
Where do I send the two cell? Yes.
in the two cells, they don't do much problem. So when you're working with the one cells, there's the problem. So R of composition of two one cell doesn't go to the composition of R of two one cells. So they are isomorphic, but not equal. So there's the pseudo functor condition comes in. But otherwise, it doesn't disturb the 0 cells and 2 cells. It plays nicely with them.
Uh-huh.
So let K be the category of enriched, category of categories enriched over permcat, that's typo, and O be an operad over K. And we now consider these two categories. So O alg ST, where the 0 cells are O algebras, 1 cells are O algebra morphisms, and 2 cells are algebra 2 cells. And O PS are 0 cells are O pseudo algebras, 1 cells are pseudomorphisms, and 2 cells are algebra 2 cells again. The theorem says the inclusion two functor from the strict algebras, operad algebras, to the pseudo algebras has a left two adjoint strictification functor, which goes from O PS alg to O algest. And the unit of the adjunction is an internal equivalence in the pseudo algebra category. So our strictification strategy will be to view the Burnside two category EG as an operad algebra or a pseudo algebra, and R as an operad pseudomorphism, and we will apply the strictification theorem to get a two functor. So just let me go back to this. So we want to see GE and GE op as elements here, and the arrow between them elements here, and we just want to shift the whole thing to that side. So how do we do that? Go a little bit to algebras over colored operads. So let C be a set. There is a C cross C colored operad OC, such that OC algebras are two categories with object set C. So we kind of trying to fix the object set. So we know both EG and EG op have same object set, and we try to use this property there. So morphisms are object preserving two functors between them, and this operatic perspective is due to Caviglia. And now apply the definition. Okay, and a similar thing holds for the pseudo algebras as well. So they correspond to bicategories with object set C, and morphisms between them are pseudofunctors, which are object preserved. So what do we do in our case? We will take the colors C to be the object set of EG. C is finite sets of the form N alpha. And also recall that our R is object preserving. So it perfectly fits into the situation of our theorem. So our final step is apply this functor to R star to get, apply this functor to the setup to get a functor R star. Note that even though R is a pseudomorphism, our EG and EG op are not bicategories. They are strict two categories. So that helps in some ways. So this is the story. Some issues that we need to resolve. So strictification theorem scope. So the strictification theorem is actually not stated for colored operads, it is stated for operads. So we need to verify whether this can be extended to that. And the context of the theorem is formulated for internal categories, not enriched categories. So we need to do a little bit of work there to see how it fits. And another thing is what Morgan was asking. So the strictification theorem gives R star between the strictified version of EG op and EG, not from EG op to EG. So the theorem in Guillaume, Marling, and Osorno's paper, even though that is in the operatic version, not colored operatic version, it says that if the two categories that we are dealing with are already strict two categories, not bicategories, then internal equivalence of, the unit is actually a morphism in the strict algebra category, not a pseudo algebra category. So that is our hope to resolve this issue. And some references are actually the whole background of this problem, and the open problem itself was given in the book Homotopy Theory of Enriched Mackey Functors. This is by Johnson and Yao. There are some the inverse equivalence of homotopy theories. The condition that is there is by Johnson and Osorno. The paper theory for two categories. The strictification theorem is from the paper Symmetric Monoidal G Categories and their strictification. This is by Guillaume, Marling, and Osorno. And the colored operatic version of two categories is from the paper A Model Structure for Enriched Colored Operads by Caviglia. So I'll end my talk here. Thank you.
Questions? Go ahead.
So I see that having something strict is probably harder or needed to work with. Is there something beyond that why you really want it to be strict?
Which one?
Like why do you want this functor to, like, why do you want to strictify it? Like, is there a...
I want a functor from EG up to EG, but the functor that I'm trying to extend from the burnside 2 category is not a real 2 functor.
Like, I guess my question is, like, why is it so important to have a 2 functor compared to
I'm trying to establish an equivalence between C and D, and I would like to have a functor, not a pseudo functor. A pseudo functor will give maybe a weaker version of some equivalence, so I'm trying.
for the presheaves setting?
Other question?
Yes. But
Why is it called burnside? Like this guy called burnside? No.
yes, there is a guy, but it
Okay.
is called after him, but I don't know.
Because Burn Cat is such a fire name, you know?
Is, do you know of like a framework for thinking about sort of EG as an infinity two category, for example? And have you thought about these sort of questions?
I'm just entering this world of infinity category and higher categories. So I don't know how to think of EG as an infinity category. Well,
I mean, I don't know because I don't work on infinity two categories or infinity one categories, but I wonder if maybe some of these strictification problems might have different solutions in like an infinity two category setting. Maybe other people here.
okay. Let's
Do you have any thoughts so far about how to generalize the Guillemet Merlin Sorner results to colored operands?
Oh, no, I haven't yet started working on that.
That's fair. I was just curious. Yeah.
Any further questions? Let's thank our Parajita again. And our next talk will be at 4. We have refreshments, although I'm not sure if they're out there quite yet. So, you know, stick around and we will turn it on. At least tea and coffee.